Okay, so welcome to this lecture, and in the last lecture we started discussion first with EG bound on the largest eigenvalue, and then we established that there always exists a non-negative eigenvector corresponding to the largest eigenvalue of a graph. Okay, and then I think suppose a non-negative vector is given, if there are entries, some entries are 0, that will imply that graph is disconnected. Okay, now carrying the study forward, today we will see some very crisp result about the largest eigenvalue and corresponding eigenvector when the graph is connected. Okay, so this again follows from Perron-Frobenius theory, which is, and for our purpose we will restrict it to non-negative symmetric matrices. Okay, so let me first write the statement, and then the statement has actually I think 4 to 5 small results, and we will prove each and all these, each of these results. Okay, so let me first write it. Okay, so okay, let G be a connected graph on n vertices, okay, and suppose x be some eigenvector, or let x be an eigenvector corresponding to the largest eigenvalue. Okay, and basically what I will write now 4 to 5 small legend, and which at the first glance it looks like that they are obvious, but I mean, please do not make any mistake to treat them as an obvious. Okay, so let me state this, and I will be using AG will be the adjacency matrix of this, adjacency matrix of corresponding to largest eigenvalue of the adjacency matrix AG. Okay, let me first write the first one. The first one is very simple. All the entries of x here are non-zero. Okay, first one is. Second one is, let me call it lambda 1, lambda 1. Okay, B of lambda 1 is 1. Basically it means that lambda 1 is not repeated at all. Okay, so maybe I can write is just like, rather than this 1 is 1. Okay, the third one is, my screen has some, yes, sorry about this. Okay, the third one is all entries in x are the same sign. Okay, so till now we have seen there are 2 more. Okay, and if for some non-negative vector, if non-negative vector x, if Ax equal to non-negative vector x, if if is repeated, this happens, ax equal to lambda x. Basically, if this vector x is eigenvector corresponding to some eigenvalue, then this eigenvalue is indeed the largest eigenvalue. Okay, then okay, and the last statement is the largest eigenvalue or so basically let me just state this as follow. So lambda 1 has the largest absolute value among all the eigen values of A or AJ. Okay, so let me again quickly state what this. So suppose we have a connected graph. This theorem is all about telling about the largest eigenvalue and the corresponding eigenvector. Okay, so firstly, all the entries of x are non-zero. Is it obvious? We will see it. Okay, the multiplicity of lambda 1 is 1. That means lambda 1 is unique. Okay, not repeating at all. All the entries of in x have the same sign. This will also be not difficult to prove. Okay, very good. If for some x, if for some non-negative, for some this is non-negative. Okay, it's always good to so non-negative. So some non-negative vector x, if that vector is an eigenvector corresponding to some eigenvalue, this implies that that eigenvalue indeed is the largest eigenvalue. Then last is lambda 1 has the largest absolute value among all these eigenvalues of AG, which essentially means, suppose that means if lambda n is the largest, is the smallest eigenvalue, if the is the smallest eigenvalue, we have to prove that, then we have to prove that lambda 1 is indeed greater or equal to mod of. So these two statements are same. Okay, so let us now prove one by one all of these sentences. Okay, or statement. Okay, so first, all entries of x are non-zero. I think this should be, we can have some intuition from the previous result in the last lecture. Okay, so suppose, so what we have to prove, all the entries, yeah. So we have given that ax is equal to, rather than, because I am using x here, right, I think I should use here y, right, so that you guys are not confused. So I'm sorry about that. Okay, so this is, I can simply say y. Okay, very good. Now I think I'm not using it. Okay, now it says that all the, yeah, this is given to us. Okay, now let me make a vector v which is mod of x. Now v is what? V is a non-negative vector, right? And we can indeed prove that this vector will also be eigenvector of A. Okay, so we have actually seen that basically, so this will imply that x transpose Ax is equal to lambda 1, right? And lambda 1, if you see it carefully, is always greater or equal to, again making mistakes, v, right? Av, and which indeed is greater or equal to this mod x transpose. Okay, yeah, okay, and which is equal to lambda 1. So lambda 1 is greater or equal to lambda 1. That means what? That means was, this is a equality here. So lambda 1 is v transpose Av, which implies that v is basically an eigenvector corresponding to lambda 1. Okay, this we have already seen it, I mean in the last lecture, but we have also seen that. Suppose there is a non-zero eigenvector corresponding to the adjacency matrix, then and corresponding to the largest eigenvalue. Sorry. So if there is a zero in V, right? That means the graph is disconnected. But we have taken graph to be connected, right? We have graph to be connected. So that will imply that all the entries in V are positive. Sorry, not positive. Maybe non-zero is correct word. Non-zero. In fact, here they are positive because we have taken modulus. So are non-zero. Hence, all the entries in X are non-zero. Very simple. Very simple. Okay. Now let us move to the next result. Next result is the multiplicity of lambda 1 is 1. Okay. So we can prove it uses, let me polish it now. We can prove it using again contradiction. So suppose there exists basically so lambda 1 is repeating suppose 2 times. Suppose lambda 1 is repeating, suppose is repeating at least 2 times. Okay, and due to spectral theorem, there exists 2 independent eigenvectors, or in fact 2 orthogonal eigenvectors corresponding to lambda 1, right? Because lambda 1 is repeating at least 2 times, so I can pick any two vectors which are linearly independent. Suppose these 2 eigenvectors are x1 and x2. Okay, so now due to our first result, right? So these all x1 has all the entries are non-zero there. X2 also will have the all entry non-zero. So I can actually cook one vector such that I can multiply x2 with a constant such that some entry or at least one entry of this vector x is 0. Right, I can always do that. I can choose some suitable constant here and I am multiplying that constant with that vector, so that if you subtract with x1, the resulting vector have at least one entry non-zero. Okay, at least one entry 0, sorry, at least one entry 0. Okay, now you see that this is nothing but a linear combination. Like, so x will also be, so x will, this implies ax is equal to lambda 1x. So let be eigenvectors independent or orthogonal corresponding to lambda 1. Okay, so and then ax is equal to lambda 1. Okay, so this will also be true, right? Because x is a linear combination of 2 eigenvectors. Okay, very good. Now what? And now you see that in this equation x cannot be 0, x cannot be fully 0. Why? Because x1 and x2 are linearly independent, right? So this cannot be fully 0. So x is indeed an eigenvector, but in this eigenvector there are some entries 0. Okay, with the and due to 0, which due to the first result. Okay, we have proven that if there are 0 entries, right? I mean, there cannot be 0 entries, right? Under the condition that the graph is connected. So this will give you a contradiction. But so x is an eigenvector of lambda 1, but it has what? A 0 entry, which contradicts one. Okay, so our assumption that lambda 1 is repeating is incorrect. Okay, so this implies that lambda 1 is unique. Okay, very good. Now third one is what? All these basically all the entries. Third one is all the entries in X have the same sign. Okay. Okay, suppose X is that eigenvector. Yeah, it is given. So suppose again, let us take Y equal to mod X. Right. We have proven that Y is also just proven that Y is also an eigenvector, right? And just some mistake. Is also an eigenvector for lambda 1. Okay. Now just due to these two guys, Y and X must be linearly dependent because lambda 1 is unique, right? So Y and X must be dependent. This is only possible when Y equal to some constant time. I mean, you can safely say either Y equal to X or Y equal to minus X, right? Okay, to some due to some constants. Okay, and then, but you know that Y is what? Y is all positive. Y is strictly positive when the graph is connected, right? So hence, so X will be what? So Y has all the basically all the positive numbers. So X will have either all the positive or all the negative. Okay, so thus I mean, I would say thus all the entries in X will have the same sign. Okay, very good. Okay, the next result is what? 4, right? If for some non-negative vector y, if this happens, a y is equal to this, then lambda is indeed equal to the largest eigenvalue. Yeah, so suppose lambda is not equal to lambda 1. Okay, and y is that eigenvector corresponding to lambda, right? In that case, what will happen? Because these two guys are different, so that means we have seen that they must be, and matrix is symmetric, so X transpose Y must be 0. Okay, now what? This implies that this is 0, right? But we know that what? X is all the entries that all the entries in X have the same sign. This implies some entries in Y must be negative. Otherwise this cannot be 0, right? X transpose Y will not be 0. Okay, but it is given that Y is not negative vector, so this is a contradiction. This is a contradiction. And so lambda indeed must be equal to lambda 1. Okay, very good. So I hope this is also very, very simple. Okay, now the last result is what? We have to prove that the largest eigenvalue have basically the largest absolute value among all the eigenvalues. Basically we have to prove that lambda 1 is indeed greater or equal to this. Okay, how can we prove that? So suppose Y is some eigenvector corresponding to lambda 1. Suppose AY equal to lambda 1 y. Okay, so we can actually write this as follows. So lambda n is what? lambda n is what? So you can actually safely write here y transpose ay. Okay, now if you take mod of this, right, now this quantity is always less or equal to if you take this, right, because A is non-negative matrix, right? Okay, now this quantity is always greater or equal to, because we have seen that, right, lambda 1. You assume that all these vectors we are taking as unit vector, right? So nothing changes here. Is this all done? And I think yes, this is done, right? Yeah, so that implies, this implies lambda 1 is always greater or equal to this number. So that means lambda 1 has the highest modulus, highest absolute value. Okay, so I am pausing it here. Now in the next lecture we will see more interesting stuff. So I mean, you might see what's the result I wrote till now were very, very simple one, but please do not make any mistake of taking these as obvious one, right? Because a small mistake can actually may result in proving some disaster result. Okay, so so please take these seriously, okay, and see you in the next lecture. Yeah.